Okay, so these are solutions to some IB questions about error, sig fig, uncertainty, and mole conversions. Question 30. So an experiment to determine the molar mass gave the result of 60 grams per mole, and the literature value is 56 grams per mole. What was the experimental error expressed as a percentage? So the error is 4 grams per mole. So the error is just how much difference is there between what the student or person got in the experiment compared to the literature value, which is like considered to be the true value or the accepted value. And then we want to express that error as a percentage. So we take the thing we want to express as a percentage, the part, we put that on top, and we divide it by the whole value. And the whole value is the true value, so we want to use 56, not 60. You've got a calculator now on paper 1, so 4 divided by 56 gives you 0.0714. Now, if we want to make that a percent, we multiply it by 100, and so we get 7.14%. And so our best answer here is going to be B. Okay, moving on. This one hits you with a number of different sig fig things all at once. So a mixture of calcium carbonate and magnesium carbonate is prepared by mixing 8.36 grams and 7.64 grams. The total mass of the mixture should be reported to X significant figures. Okay, so first thing to realize is that you're doing addition. It's kind of a trick question because when you add things, you actually don't round off based on significant figures. You round off based on number of decimal places. So because both of these numbers have 2 decimal places, when I add them and they add up to exactly 16, I actually need to keep both of these decimal places. So I'm not going to round it to 16.0 based on sig figs. I'm going to keep 4 significant figures around because the rule is I have to keep 2 decimal places because both of these numbers have 2 decimal places. So right away, I know that A is wrong and D is wrong because my first answer has to be 4. Okay, next, the mass ratio of calcium carbonate to magnesium carbonate should be reported to Y significant figures. Now, a mass ratio is like when you divide things. Now, I'm not even going to bother dividing them because they just want to know the number of sig figs. And I know that when I divide, I round based on the lowest number of sig figs. Well, both of these have 3 sig figs, so the second answer has to be 3, which means B is wrong. And if this is multiple choice, I would move on at this point. I wouldn't even figure out the final answer. We can do it anyways just to be sure. The difference in mass between the two should be reported to X significant figures. Okay, sort of another trick here because, again, when we subtract, we're going to round and make sure that our answer has 2 decimal places. 8.36 minus 7.64, and the answer is 0.72 grams. That's the difference, and we're going to keep those 2 decimal places, which means our answer only has 2 sig figs, not 3 like the answers, the values that we're using in the calculation. So the answer has to be C. That's a nice, probably more involved question than most IB questions. This question comes from In Thinking, the support service for the IB. It's similar, but I don't know if they'd ever have you do those 3 things within one multiple choice question. Okay, moving on to 36. A thermometer with an accuracy, I would maybe say a precision of plus or minus 0.2 degrees Celsius was used to measure an initial temp of 25.4 degrees Celsius and a final temp of 18.4 degrees Celsius, which is the correct way to record the temperature drop. Well, I can tell it's gone down 7 degrees, and you see that's not really the issue. All of them have recognized that the change is 7 degrees. If we're going to do subtraction, we would keep 1 decimal place, so 7.0. That's one reason why we should report it as 7.0 and not just 7, if we're following sig fig rules. But really, now we have to think about the uncertainty rules. So if each of these temperatures was plus or minus 0.2, whenever we use 2 values with uncertainty in calculation, we want to add those uncertainties together. And since we're doing subtraction, there's no change in unit, we can just keep it together as 0.4, combine them, add them together as 0.4 degrees Celsius. So that's going to be our answer. So we're following our uncertainty rules here. when subtracting, we can simply add the two uncertainties together to get the total uncertainty. 37, a piece of metal with a mass of 20.000 grams was placed in water in a graduated cylinder, and the water level was observed to rise from 34.4 centimeters cubed to 39.4 centimeters cubed. What's the correct way to report the density? So density is mass divided by volume, and I can see that the mass is 20 grams. It's got 5 sig figs, and the volume, when I do that subtraction, is going to be 5.0 cm cubed, and that's based on the 1 decimal place in each of those volumes. So this volume has to have 1 decimal place also. So I've got a 5 sig fig on top and a 2 sig fig on the bottom, which means my answer is going to have 2 sig figs. And so the best answer is B. Notice all the answers are 4. 20 divided by 5 is 4. And so really, it's just a question about sig fig rules. Okay, if I move on to question 40. What amount of atoms in moles is present in 128 grams of sulfur dioxide? So sulfur dioxide is SO2. Hopefully I have added something to the assignment post so you realize that. Okay, and sulfur has a molar mass of 32 grams per mole. Oxygen has a molar mass of 16 times 2, it's also 32. And so our total molar mass is going to be 64 grams per mole. All right, well, if I have 128 grams of sulfur, even without my calculator, I can see that that's twice as big as the molar mass. So remember, the molar mass is the mass of 1 mole. Another way to write molar mass is 64 grams per 1 mole. Okay, well, if I have 128 grams, that means I must have 2 moles. Okay, so that's the moles of SO2. Okay, now let me shrink all this down so we have a little more space. The question has asked me for the number of atoms, so the actual number of atoms. So right now I know that I have 2 moles of SO2. Now the next step is to get it from moles to particles. That's where I use Avogadro's number. So I know that there's 6 times 10 to the 23rd molecules of SO2 in 1 mole. And I said molecule because I can tell that SO2, that's made of 3 different atoms, so it must be a molecule. It's not an atom. So I've rounded off here. This is a sort of non-calculator approach. So 2 times 6, that would give me 12 times 10 to the 23rd molecules. Okay, but the question didn't ask for molecules. The question asked for what amount of atoms. And now I can count that within each SO2, there are 3 atoms. That's the ratio. There's 3 atoms in 1 molecule. So this is the number of molecules. I have to multiply this by 3 because there's 3 atoms in every 1 molecule. And so 3 times 12, I would get 36 times 10 to the 23rd. And I can convert that with proper scientific notation to 3.6 times 10 to the 24 atoms. And so the answer's got to be B. 41. How many molecules are present in 27 grams of distilled water? Distilled water is just pure water, so we're dealing with H2O. Hydrogen weighs 1, so there's 2 hydrogens, which weighs 2, plus oxygen, which weighs 16. We've got a molar mass of 18 grams per mole. We've got 27 grams. 27 divided by 18 gives us 1.5 moles. Okay, and now I want to convert that to molecules. So this is the moles of H2O. Water is a molecule, so I'm simply being asked how many particles is this? 1.5 moles of anything is 1.5 times Avogadro's number. So 1.5 moles times 6 times 10 to the 23rd, and we get 9 times 10 to the 23rd. That's the number of particles. So I don't have to do an extra ratio step because I've been asked about molecules. Water's smallest particle is a molecule, so I'm all set, and the answer is C. Okay, now one where they say, what is the total number of atoms in 3 molecules of this thing, propanone? Okay, so this is a question where I'm going to have to use that ratio again. What's a little unique about this one is they didn't start me with moles like they normally do. They said just in 3 molecules. Okay, so I only have 3 molecules. So let's count. In this formula, there's a C, that's 1 atom. Then there's H3, so 1. Then there's 3 hydrogens. Then there's a carbon, plus 1. Then there's an oxygen, plus another 1. And then there's a C, plus 1. And then there's 3 more H's, plus 3. If I add all those together, there's 10 atoms in this 1 molecule. Okay, so how many atoms are there in 3 molecules? Well, 3 times that much, so there's 30. I should be able to eliminate these 2 answers if I read carefully and realize that I'm only dealing with 3 little tiny molecules, so I'm not going to have some crazy amount of atoms. If they had said 3 moles, yes, then I would have one of these. I'd have a really big number of atoms. But because I'm only dealing with molecules, a couple of molecules, I'm going to have a relatively small number of atoms. Okay, last one for the homework. Which sample contains the least number of atoms? Okay, so this is a way they make you do more than one calculation within one question. This question is really all about ratios and recognizing that when you know about the number of moles, that is as good as knowing about the number of particles. What do I mean by that? Okay, so I've got 2 moles of NaCl. How many atoms are in each NaCl? Well, there's 1 Na and there's 1 Cl. So if I've got 2 moles of NaCl, I've got 2 atoms per particle, per molecule. And so I've got 4 moles of atoms in this first one. So all I have to really do is these ratios. If I know about the moles of atoms, that's as good as knowing the actual number of atoms. And so sometimes you can save yourself a lot of work if you just really understand this mole concept. It's like saying, I've got 2 dozen bikes, so that means, well, in each bike there's 2 tires. That means I've got 4 dozen tires, right? Now I could go on and figure out that 4 times 12, that means I've got 48 tires, but knowing how many dozen tires I have is also a way of knowing how many of them I have. So we can skip the step here where we times 6 times 10 to the 23rd, because that just adds extra math. What we're eventually going to hopefully get to is that knowing numbers of moles is just as good as, and it's actually a lot simpler than knowing the exact number of atoms. Okay, let me keep going to show you what I mean. In this one, in NH3, there are 4 atoms, 1 N and 3 H's. So in this one, there's 4 atoms per every molecule. That's our ratio. And I've got 2 moles, and times 4 atoms per 1, that means I've got 8 moles of atoms. In this next one, I've got C plus 3 H's is 4, plus 1, 2, 3, 4 atoms there, so there's 8 atoms. 8 atoms in 1 molecule, and I got 1 mole, so 1 times 8, I've got 8 moles of atoms again. So we can already see that B and C are both wrong because they are greater numbers of atoms than the first one. And the last one, 1 mole of H2O. In H2O, there are 3 atoms per molecule. So if I have 1 mole of water, I have 3 moles of atoms. And 3 moles of atoms seems to be the lowest number. So 4 is too high. Therefore, the answer is D.